So uh, what I want to do is I want to teach you how to read this. I don't know if you can actually read it, but the Xerox came that way. So if you're having trouble, you can talk to me, and I will see if I can try to get a more lucid or clear version. But we'll just work with this now. First of all, you can bring this to the test. Okay, so bring this to the exam. I'll try to make sure I have extra copies for the exam. Bring this to the test. This is not something you need to memorize. And let me explain to you guys how to read this. So this is called the standard reduction potential table. And I have extra copies here if you need it for the test, if you want to make notes on it and use that for the exam, or if you want a fresh copy for the exam, that's okay. I can print out many of these. What I want to focus your attention on is reduction. Okay, so can anyone tell me what happens? Where does reduction occur? Does it occur in the cathode or the anode? Excuse me. Cathode or the anode? Cathode. Very good. Cathode. Okay, remember red cat. So all of these reactions would, if we're half of a battery, and if they were to serve as a battery, they would serve the half of a battery that is called the cathode. Okay, where reduction happens. All right. So that's number one. Okay. First major point here is that all of these are reduction half reactions. Okay, key word is half reactions. Okay, reduction, because reduction half reaction. So these occur at the cathode. Okay, these are reduction half reactions. So in a reduction reaction, half reaction, half. Okay, half reactions. Where are the electrons? Are they in the reactant side or the product side? Reactant side or product side? Reactant side. Okay, so you can see here, let's take a look at this first example. F2 gas gains 2 electrons. All right, let's look at this example here. Cl2 gas gains 2 electrons. Okay, how many electrons is being gained by Ag plus here? How many electrons? 1. Okay. So all of these are cathode half reactions. Okay, all of these are reduction half reactions, and all of these are where the substance gains an electron. Okay. And so these are the voltages associated with that reduction. So these are reduction half reactions. You want to give these reach. I was testing your flexibility. Oh. All right, so all of these are gaining electrons. They are reduction half reactions, and this is the voltage, standard voltage. Okay, standard. Another key word here is standard. Okay, so that's why you have not just E, but E naught. Okay, E naught. And what does the V stand for? What are the units? Volts. Okay, because we're talking about a battery. Okay, one half of the battery is the cathode, the other half is the anode, but here these are all cathode reactions. This is standard reduction potential. Potential is just a fancy word of saying voltage. All right, all right, so that is, actually I'm going to call this E standard state of the cathode. Okay, because these are all cathode reactions. All of these are reduction reactions. Okay? So that is point number one I want you guys to know from this. Okay? All of these are reduction half reactions, E cathode standard state, the standard state voltage. All right. Point number two I want you to know is that if you flip this reaction, let's take a look at this reaction for a second here. Okay, I'm going to write it here. I'm going to take this reaction and I'm going to rewrite it on the side. Okay? So this has an E standard state voltage of plus 2.87 volts. Okay. All right. What I'm going to do now is I am going to flip this reaction. Okay. Let's say we flip the reaction. Okay. If I flip this reaction, okay, the 2F minus becomes reactants, F2 gas plus 2 electrons becomes product. If I flip this reaction, this is no longer E cathode, but what will it become? Instead of gaining 2 electrons, what has happened? Instead of gaining 2 electrons, it has lost 2 electrons. So what is losing 2 electrons? What is that called? Leo-Ger, lose electrons oxidation. So this is an oxidation half reaction. Where does oxidation occur? The cathode or the anode? Anode. Okay. So now this is minus 2.87 volts. Okay. Right, so if you flip a reaction, you flip the sign. And as you flip the sign, what was once reduction becomes what? Oxidation. So if you flip the sign, the cathode becomes the anode. All right. So which do you think is more likely to happen? Positive 2.87 volts or negative 2.87 volts? Okay. Positive or negative? Positive, right? Positive 2.87 volts. What type of batteries do you buy? Do you buy them positive volts or negative volts? Okay, so we're going to call this something that is spontaneous. Okay, the negative voltage would be what? Non-spontaneous. So negative voltage is a dead. Okay, we don't have such a thing as negative voltage. Okay, the batteries on this, the batteries on the remote, they're all positive voltages. So this would be non-spontaneous. Yeah. Okay. All right. So positive voltage is a good thing. Okay. Negative voltage is something that just doesn't happen. It would be a non-spontaneous. So I guess what I'm trying to say is if you see a positive voltage, this would favor the products because positive voltages, are something that is spontaneous. That is something we see. We don't see negative voltages. So if it's a negative voltage, then it favors the reactant. This reaction is not happening because it's negative voltage. This reaction is happening because it's positive voltage. Just think everyday life. Okay, I go to Walmart, I buy what? Positive voltage, 9 volts? Or do you buy negative 9 volts? Or whatever voltage. Okay, you buy positive voltages. So the positive sign means it's something that favors the products. The negative means it favors the reactants. It's a reaction that's not favored to go. All right, the next rule here is kind of important. Okay, so let's say I take this half reaction, okay, with the blue dot, and I multiply it by 2. Okay, I multiply it by 2. Okay, so what happens if I take this half reaction and multiply it by 2? Okay, I'm going to get 2F2 plus 4E minus goes to 4F minus. Okay, what will be my E of the cathode? Okay. My E cathode will still be positive 2.87 volts. Okay, so this value does not change. That's a super important point. Okay, so all these numbers here, all these voltages here, let's just circle all of them. All these voltages, they are set. Okay, these numbers will not change in value. Okay, if you multiply this half reaction by 2, or multiply it by 1/2, or you multiply it by 3, okay, these numbers will not change in their value. Change in their value. Right? When will they change? What can they only change? They can't change in the actual number, but what can they change? They can only change in the sign of the number, but can they actually change the number? Okay, now can they change the sign? Okay, how can you change the sign? By flipping. Okay, and then what was the cathode? Gaining electrons, you flip it, it becomes the anode, you lose electrons. All right, so that's point number 2 here. All right, now I'm going to teach you something that's kind of a little difficult, so kind of bear with me here, okay? So you're going to pick one or any one of these half reactions, okay? I'm just going to pick this one here. Pick one, any one. I just chose this third one, or fourth one. And if we want a functional battery from these chemicals, okay, one has to be oxidized and be the anode. The other one has to be the cathode and be reduced. So how do you get a positive voltage? Okay, the one that you highlight, okay, any one, but I just chose this one can flip. In other words, this one can oxidize anything below it. And you'll get a positive voltage, because a positive voltage favors the products. So this is how you do it. You pick one and any one, and then it flips anything below it. That will give you a positive voltage. It flips everything below it. All right. As an example, can H2O2 oxidize water to 4H plus and O2 gas? Can H2O2 oxidize, flip, water into H plus and O2 gas? Okay, is the answer yes or no? Okay, can it flip it and give you a positive voltage? The answer is yes. Okay, so let's do that. Okay, I'm going to write this equation again, this half reaction. I can't find paper. Okay, you pick one, any one. Okay, we pick one, any one. I just chose this one. And what I told you is that it can flip the one below it. Not above it, below it. Because you see, if you flip above it, it becomes a negative voltage. But you pick one, it can flip anything below it. That will give you a positive voltage. So I chose this one. Okay, what is that? Positive 1.77 volts. Okay, this is the cathode, because all of these are cathodes. Okay. I chose water. Can it flip water and get it to oxidize into O2 and 4H plus and lose 4 electrons? Okay, I'm going to flip it. Plus 2H2. H2O goes to O2 gas. I'm just flipping this. Plus 4H plus 4E minus. Okay, what do we do when we flip a reaction? We flip the sign, so it's minus 1.23 volts. We flip the reaction, the cathode becomes the anode, besides flipping the sign. Let's add these two up. Okay, it just so happens the one I chose, these two waters will cancel, and H2O2 plus 2H plus 2E minus goes to, actually before we do that, I'm going to cancel out these electrons by multiplying this by 2. And then this will give me 2H2O, 2 plus 4H plus 4 electrons goes to 2 waters, actually goes to 4 waters. Okay, I'm just canceling out these electrons here. And then this I'll leave as 2H2O, O2 plus 4H plus 4E minus, okay? If I multiply by this by 2, it's still positive 1.77 volts. Okay, because these numbers never change. The only thing that changes is their sign. So these numbers will never change. The only thing it will change is their sign. And what I told you is that this, whatever one I choose, can flip everything below it. It flips everything below it. So I wrote this. I flipped this because I want to convince you that this can oxidize water into oxygen and 4 protons. So I take this, I flip that, I multiply this by 2. Okay, I wrote this, I flip that reaction, I multiply this by 2 to cancel out the electrons. 4E cancels, 4H plus cancels. We are left with 2H2O. And my net reaction is 2H2O plus O2. And then we add the cathode and the anode, and this is going to be 0.54 volts. Positive 0.54 volts means it favors the products. Okay, so you can make a battery with H2O2 being reduced to water and water being oxidized to oxygen. So, positive voltage means this is a fully functional battery. Okay, let's do one more example. Okay, I pick one and any one. Let's go with this one. Can H2O2 oxidize Fe plus 2 to Fe plus 3? Can it do that? Yes or no? Can it oxidize Fe plus 2 to Fe plus 3? Okay. Yes, can it or no? It cannot. The answer is yes, it can. Okay, so this can cause anything below it to flip. All right, we do that again. H2O2 plus 2H plus 2E minus goes to 2H2O. This is positive 1.77 volts. This is the cathode. Okay, does it flip this? If we flips it, it's Fe plus 2. Okay, we flip it, goes to Fe plus 3 plus an electron. Okay, because this has flipped, what do we do with this voltage? We flip the sign, so positive 0.77 becomes negative 0.77. This has lost an electron, so it becomes the cathode, it becomes the anode, excuse me. I'm going to cancel out the electrons. To cancel out any spare electrons, I'm going to multiply this bottom part by 2, this bottom half reaction. So let's rewrite everything again. Okay, remember, these values never change. These values never change. The only thing that changes is their sign by flipping it. All right, so this is still at positive 1.77 volts. This is minus 0.77 volts. This is gaining an electron, so that is reduction, which happens at the cathode. This is losing 2 electrons, which is losing 2 electrons, which is oxidation, which happens at the anode. And then we cancel out our electrons, and yes, H2O2 plus 2H plus 2Fe plus 2 gets converted to 2Fe plus 3 plus 2H2O. Okay, you add the two reactions, you add the voltages, and what will you get? 0. A 1 volt battery. Okay, a 1 volt battery. So the question is, can H2O2 oxidize Fe plus 2 to Fe plus 3? Yes, it can. Okay, whatever one you pick, anything below it can get oxidized and will still give you a positive voltage. Okay, and remember, positive voltages favor the products. Okay, do we understand this? Okay, so we just pick one, any one. Okay, let's pick this one here. Can copper oxidize nickel to nickel plus 2? Yes or no? Can copper oxidize nickel to nickel plus 2? What do you think? Yes or no? Remember, if you flip it, it becomes what? Oxidation. So can copper plus 2 oxidize nickel to nickel plus 2? What would the answer be, yes or no? Yes. Okay, you pick whatever one. Anything below it can get flipped. Okay, this is called the diagonal rule. This is also called the activity series. Which one is better at gaining electrons? Which one is better at losing electrons? Okay, so copper plus 2 can oxidize, that means flip, oxidize nickel to nickel plus 2. Okay. But, okay, listen carefully to this because it gets kind of confusing. While you pick one and it causes anything below it to flip, what about anything above it? Okay, it cannot. Okay, do you want a positive voltage? Okay, then it will oxidize anything below it. Do you want a positive voltage? You pick one. You keep the one above the same. You don't flip it, but what do you do to the one you choose? What do you do to the one you choose? You flip it. Okay, that's how you get a positive voltage. Okay, so what are the two ways you can get a positive voltage and a successful battery? All right, you pick whichever half reaction, and then anything below it, what can it do? It can oxidize it. It can oxidize it, so anything below it will get flipped. Okay, what about anything above it? Can it get flipped? Okay, what will you flip then? Which one? You flip it. Not the one above, you flip it. Good one. You flip it. Okay? And the one above, you keep the same. Okay? These are the two ways you can get a positive voltage. All right. So let's go over this again. So can copper, this same copper here, can copper oxidize 4OH minus to O2 gas? Can copper oxidize 4OH minus hydroxide to O2 gas? Can it do it? Yes or no? No. Okay, it cannot. Okay, so going this way, it cannot. Okay, going this way, it can. All right. Are we understanding our interpretation of this activity series? Okay. Let's just do one more here. Can zinc, everybody knows zinc, right? Can zinc oxidize magnesium to Mg plus 2? Can it oxidize zinc? I'm sorry. Let me repeat this. Can zinc plus 2 oxidize magnesium to magnesium plus 2? Yes or no? Okay, the answer is yes. Can it? Okay, you'll get a positive voltage. But can that same zinc oxidize nickel to nickel plus 2? Can it? No. Okay, no. Okay, so that's what you can do. It can flip anything below it. Let me see if I can use these markers. Okay, so this direction is yes. Okay. The other direction above it is no. So this is how you read the activity table. Okay, so if it flips anything below it and oxidizes it subsequently, you'll get a positive voltage. Okay? If it flips everything above it, the one you choose, it, okay, flips everything above it, and that stays the same, that's a negative voltage. But okay, if you keep everything above it the same, don't change it, don't flip it, it's still cathode, and flip it to the anode, that's how you get a positive voltage. So this is how you read this thing. Okay, and remember, these numbers, will you ever change? What can you only change about all these numbers? This whole column of numbers, what can only change? The sign. Okay, so if you multiply this reaction by 5, what's the voltage? Still 0.2. If you multiply this reaction by 3, what's the voltage? Same. Okay, these numbers will never change. All right, let's look at the topmost two. Okay, let's look at this one here. This is the most positive. Do you see it? So what do you think this half reaction favors? The products or the reactants? Products, very good. Okay, so this is a very spontaneous half reaction. F2 gas gaining 2 electrons to 2F minus. So we call this the best oxidizing agent. It is the best. Okay, it's the best oxidizing agent because it has the greatest tendency to become reduced. Okay. Remember, the oxidizing agent is the agent that causes, that itself gets reduced, but causes your oxidation. Okay. So this gets reduced, so that means it's very good at oxidizing someone else. And you can see here, this can oxidize everything below it and give you a positive voltage. So it's the best oxidizing agent. Okay, remember, what do we say? We pick one. If we were to choose this one, it can flip anything below it and give you a positive voltage. Since this is at the top, it's the best oxidizing agent. Okay, it's very good at oxidizing you, Allison, you, Leslie, you, everybody. Okay, you, Michael. It's very good. Okay, and when it oxidizes you, and me, what it does, it gets reduced. So it's very good at oxidizing you and itself getting reduced. Okay. Okay, let's go all the way to the bottom here. Okay. So we have here lithium plus 1 electron goes to lithium solid. That's minus 3.05 volts. Okay. So minus 3.05 volts, is that a spontaneous or non-spontaneous process? Negative 3.05 volts. Good or bad? Non-spontaneous. So this is something that's not likely to happen. Okay, we don't have negative voltages, so this is non-spontaneous. Okay, so we say lithium at the bottom is the best reducing agent. Because it's very good at what? What can you do with this? Keep everything above the same and do what to it? flip and oxidize it. Why? Because if you flip it and oxidize it, what will it become? Positive 3.05 volts. Okay, so we choose this. So you notice this is very good at keeping everything above the same. All these will stay the same. You don't flip it, but itself will get flipped to positive 3.05 volts. That will give you a positive voltage. So this is the best reducing agent. Okay, it has the greatest tendency to become oxidized and very good at reducing you, me, everybody. Okay, itself getting oxidized, because remember, oxidation will yield 3.05 voltage of potential. Okay, so this is the best reducing agent. Okay, it has the greatest tendency to become oxidized. Okay. So this is very good at keeping everything above the same and itself getting flipped. This is very good at doing what? The opposite, flipping everything flipping everything what? Below, and then itself staying the same. Okay, so once again, you pick one, any one. Okay, the one you pick, everything below it can get oxidized. Everything below it can get oxidized. Everything below it can get flipped into the anode. You pick one, any one of these half reactions, anything above it cannot get flipped. Anything above it stays the same. What do you do to it? You flip it. Okay? So this is how you read this table. It's called standard reduction potential. It also is called the activity series. So bring this to the exam, and we'll move on to page 2 of our notes. Do I have page 2 of our notes? Where are my notes? Okay, who took my notes? You did.
You gave me a copy, but it was like a blank copy.
I have it somewhere in this mess that you call a thing, but I can use that, and I'll give it back to you. All right, let me just give 2 more minutes here. It'd be strange. Why would I just take 1 page, not anything else? Well, you know how it works, right? At the end of the class, it shows up. So. Here's my chapter 17 notes. We'll keep that here. Standard reduction potential here. And here are my notes.
Totally write all my notes.
Huh?
Fine. So you would totally write all my notes. Okay.
All right, so make sure you are comfortable reading this. Okay, make sure you're comfortable reading this, understanding this. What can oxidize what? what can reduce what. Okay, once again, you pick one, anything below it can get oxidized. You pick one, anything above it stays the same. The one you choose gets flipped, and the one you choose gets oxidized. Okay, pick one, anything below it gets flipped. The one you choose stays the same. Pick one, anything above stays the same. The one you choose gets flipped. Okay. That's how it works. All right, so there's a notation that I'd like for you guys to know here. Okay, this is right here. Okay, so you do an anode couple, salt bridge, cathode couple. So this is what I mean when I say that. Okay, so you take a zinc electrode, zinc solid. Okay, and it's in a bath. Okay, the bath contains zinc sulfate. Okay, that's dissolved in water. Okay, total separate end, another beaker, separate. These are not communicating with each other, these two beakers. You have a copper solid, copper strip, and it's floating in a bath. Okay, this bath contains copper and SO4 minus 2. Copper plus 2, SO4 minus 2. The only thing that's joining these two together is this glass U-shaped thing. This is called a salt bridge. Okay, this salt bridge has two lines. Okay, that's the symbol. Okay, this is the symbol for a salt bridge. Okay. So what happens is that, you see, they're not communicating other than through this salt bridge, which allows ions to not build up. Because if you don't have this salt bridge, a whole bunch of ions will build up here, a whole bunch of ions will build up here. So the salt bridge just allows ions to move back and forth. But what happens, this zinc solid in contact with this zinc sulfate, is that this zinc solid in this bath will actually lose 2 electrons, okay? And the 2 electrons travel up this wire. Okay, they travel up this wire. They register a voltage. They go down this wire, and they will reduce or be gained by the copper. Okay, so the electrons are going to go from the zinc through the wire and into the copper. The electrons from the zinc solid will go through the wire, down the wire, and into the copper solid. Okay, this zinc is in a bath that's in zinc sulfate. This copper solid is in a bath. It's in a solution of copper sulfate. Okay, this is a voltmeter, which measures voltage. So what's happening is that that zinc solid is getting converted to zinc plus 2. And how many electrons are lost in the process? Okay, the charge here is 0. The charge in the product side needs to be 0. That's 2 electrons. Okay, is this the cathode or anode? Losing 2 electrons. Anode, very good. Okay. And what's the voltage associated with this? Okay, zinc solid goes to zinc plus 2E minus. Okay, zinc solid plus 2E minus, zinc plus 2E minus goes to zinc solid. Okay, what do we need to do with this reaction? Okay, we need to flip it. Is this 0.75? Okay, we need to flip it. Why do we flip it? Okay. because this is what's happening here. So we flip this, it's positive 0.76 volts. Okay, these two electrons are going to be gained by the copper. So copper plus two electrons. Okay, gave you copper solid. Okay, is this the anode or the cathode? Okay, you're gaining 2 electrons, so this is the cathode. All right, what is the voltage associated with this? Do I see? Here we go. Okay. Come on. Okay, the voltage associated with this is positive 0.34 volts. Okay, so we get E cell here is 1.10 volts, and our net reaction is Cu plus 2 plus zinc solid goes to copper solid plus Zn plus 2. We always cancel out our electrons. Okay, 2 electrons cancels out with 2 electrons. This is a 2 electron transfer reaction. Okay, so you see what's happening here. The 2 electrons are leaving the zinc, and they're going to the copper plus 2. They're actually going to the copper plus 2, to be honest. Okay, and that's giving you copper solid. Okay, one is the cathode, one is the anode. This is a spontaneous reaction. Okay. Why is it spontaneous? Because of the positive voltage. All right, so this is how we depict this. Okay, what's the anode? Zinc going to zinc plus 2. So you're going to do zinc. You're going to draw one line, zinc plus 2. Okay, that's the anode couple. Okay, the salt bridge is 2 lines. And then we do the cathode couple. Okay, what's the cathode couple? Copper plus 2 to copper. So the cathode couple here is copper plus 2. You draw one line and then copper solid. So what I want to convince you is that this zinc going to zinc plus 2 salt bridge, okay, the 2 lines is a salt bridge. Salt bridge copper plus 2 to copper is the exact same thing as this reaction. Okay, so on an exam, if I give you this, you should be able to write that. If I give you that, you should be able to write this. Okay, it's the anode where oxidation happens, and cathode where reduction happens. The 2 lines, once again, represent a salt bridge. All right, we'll practice some more of this next week. So now that we got our feet wet, but the idea here is reading this table, okay, understanding how we can construct. One of them has to be the cathode, one of them has to be the anode. We flip whichever one that we need to get a positive voltage, and the symbol is the same as this net reaction.